Welcome to the second lecture in our 8th module. If you'll recall, in the first lecture, I discussed point estimators, confidence intervals, and the t-distribution. In this lecture, we're going to be talking about hypothesis testing for single group means and paired differences, and we'll also be using the t-distribution in this lecture. Okay, so what we're delving into now is the realm of hypothesis testing, and so this falls under the rubric of statistical inference because a hypothesis is really a conjecture about the nature of a population, and usually this conjecture is based on theory and prior research, and that our goal is to make this conjecture and test the sample, and based on our testing of the sample, draw an inference of whether what we're conjecturing is true of the population. When we construct a hypothesis, we're really actually constructing two hypotheses. The first is the alternate hypothesis, and this is what we're proposing to be true. And the burden of proof, statistically speaking, is placed here. It's placed on, we assume, we're not going to assume what we're proposing is true. We're going to assume the opposite is true and try to disprove that. And so we only accept our alternate hypothesis if we can reject the null hypothesis. And the null hypothesis is the status quo. This is what is already assumed to be correct or maybe shown to be correct by prior research. And we assume it unless we can prove otherwise. And so again, we place the burden of proof on ourselves in that we're assuming the status quo, and we're only going to accept our alternate hypothesis if we can prove the status quo wrong. And very importantly, it has to be the mutually exclusive alternative to the alternate hypothesis, right? If it's not true, then the other one has to be true. Otherwise, we'd just be putting up a straw man, logically speaking. So hypothesis tests estimate the probability that results obtained from the sample meet the assumption made under the null hypothesis. And so tests of hypotheses are called tests of significance. And so I'm going to walk you through actually 6 steps for hypothesis testing. The first step is to formulate the null hypothesis in statistical terms. Again, it states the current belief or what is expected or has been shown to be true in the past. Secondly, we want to formulate our alternate hypothesis in statistical terms again. So we normally assume, as I mentioned before, the null hypothesis is correct unless we can find strong evidence to the contrary. Thirdly, we want to set our significance level alpha, typically equal to 0.05, but it could be different from that. And also determine what our sample size n is going to be. We typically require strong evidence against the null hypothesis, and so that's why alpha is set at 0.05. This means that there's only a 5% chance that we would see the result that we see in the population if the null hypothesis were true. So based on our sample observation, if we can reject the null hypothesis at a level of significance of probability value of 0.05, it means there's only a 5% or less chance that we'd see the result in the population if the null hypothesis were true. So fourthly, we want to select the appropriate test statistic and identify the critical value for rejecting the null hypothesis. This is referred to as the rejection region. And so these are the values of a sample statistic, whether we're talking about the z distribution, t distribution, or f distribution, that will lead us to reject a null hypothesis. Then fifthly, what we want to do is collect our sample data and then calculate the test statistics. Lastly, if the calculated statistic falls in the rejection region, then we reject our null hypothesis in favor of the alternate hypothesis. But if the calculated statistic falls outside of the rejection region, then we don't reject our null hypothesis and we stick with the status quo. So the next slides are somewhat theoretical, but they're important because there are possible errors from hypothesis testing. It could lead to a wrong conclusion, and we're talking about probabilities here, and this is where selecting the alpha value becomes important. And there are two specific errors that I'm thinking about. The first is what's referred to as a type 1 error. This is if we reject the null hypothesis when the null hypothesis is actually true. And so that probability is actually equal to alpha. And this is why we pick a low value of alpha. If alpha equals 0.05, then there's only a 5% chance that we would reject the null hypothesis when the null hypothesis is in fact true. Some studies, they'll set it even lower at 0.01 or 0.0001. The second type of error, it's what is referred to as a type 2 error. And this is the error that occurs if we accept the null hypothesis, or the status quo, when the null hypothesis is in fact false. And this is often referred to as beta, and beta is often much higher because generally people don't consider it to be as problematic to accept the null hypothesis when it's false as it is to reject the null hypothesis when it's true. So here is a way of thinking about this type 1 and type 2 errors in a schematic. You can see we have what is really true in blue, and so in the two columns there's either an effect or there's not an effect, and then in the rows the conclusion from our test of significance, where we conclude that there's an effect or conclude that there's no effect. So if there is actually an effect in reality and we conclude there's an effect, then we've reached a correct conclusion. That's equal to 1 minus beta. If we conclude that there's no effect and there is no effect, that's also a correct conclusion, equal to 1 minus alpha. But we also have our two types of errors. And so the type 1 error, which is alpha, is where we conclude where there is no effect in reality, and we conclude based on our tests that there is an effect. For instance, say we were doing a clinical trial of a drug, and we concluded that the drug lowered people's cholesterol when it actually didn't. That would be an example of a type 1 error. And that's why type 1 errors are generally considered more serious. And so in that drug trial, they probably wouldn't set alpha at 0.05 even. They'd probably set it at 0.01 or 0.001 because you want to require strong evidence, basically, for rejecting the null hypothesis. However, there's also the possibility of a type 2 error, of concluding that there is no effect when you conclude there's no effect based on your test, but in reality there actually is an effect. So that would be the case of, the drug does lower cholesterol, but you conclude that there is no effect. Okay, so obviously the p-value of the test, alpha, is very important. And so this involves the mean or proportion that you're testing. In this module, we're focusing on the means, and then in the next module, we're going to actually talk about proportions. But here we're focusing on means, and so alpha is the probability of obtaining a mean as extreme or more extreme than the observed sample mean, given that the null hypothesis is true. As we saw before, it's the probability of a type 1 error. And so the criteria for rejecting or not rejecting the null hypothesis is based on the p-value. If the p-value of your test is less than alpha, less than 0.05, then you reject the null hypothesis. But if your p-value is greater than or equal to alpha, say it's 0.05, then you don't reject the null hypothesis. You fail to reject the null hypothesis. It's also important to think about one-tailed versus two-tailed hypothesis tests. And so there are 3 forms of a null hypothesis. Let's talk about the two-tailed test first. So if you look at the graphic there on the bottom, in the far right-hand side, that is showing a two-tailed test. And under a two-tailed test, we're assuming a null hypothesis of saying the population mean equals some given value, right? So that's at the bottom there under two-tailed, mu equals some value of mu naught. Our alternate hypothesis is just, so that's probably the status quo. Say BMI equals 25 on average in the population. Our alternate hypothesis that where we're trying to disprove the status quo is that the mean actually equals some other value. Say we just think it's BMI is different than 25. Well, it's a two-tailed test because we're not saying that we think it's greater than or less than. We're just saying we think it's different. So when you look at the distribution at the bottom, all we want to see is if the value, the probability falls out on the outer edge of those two tails. And so 2.5% on one tail, 2.5% on the other tail. That's if our p-value is 0.05. But there are also one-tailed tests. And this is where we actually are specifying a value of for the null hypothesis and the alternate hypothesis. And so the one-tailed left side test is where we're saying in our alternate hypothesis that we think the mean value is less than some specified value. So say again, we're talking about BMI in a population, and we thought based on our sample the mean value was actually less than 25. Our null hypothesis would be then that it's greater than or equal to 25. And so that null hypothesis would look on the entire upper 95th percentile of the distribution, and we would be looking just at the 5% on the lower end of the distribution. If we were making a one-tailed right side alternate hypothesis, say that body mass index was greater than 25, we would be looking for just the 5% at the upper right tail of the distribution. And so the null hypothesis would be everything included in the lower 95th percentile of the distribution. Because again, remember, our p-value of 0.05 is we're trying to say that our sample is statistically significantly different from the population. So there has to be a greater than 95% chance that it's different. And so you would, in the graphic below there for the one-tailed test, you can see that we would be looking at the upper tail. In that case, is z-score corresponding to 1.645. And so the first thing we're going to walk through for hypothesis testing is thinking about a single group mean. And the objective is just to test whether a given sample mean is outside the range of what was previously believed to be the population mean. Our assumptions are that we have a normally distributed population mean or a sample size of 30 or greater, and that our variance, sigma squared, is known. So here's the recipe. We set up our null hypothesis, set up our alternate hypothesis, choose our desired alpha value, typically that's 0.05, and then we need to identify the sample mean, x bar, the population mean, mu, the sample standard deviation, s, and sample size, n, and our degrees of freedom, equal to n-1. And then we want to identify the critical value of the t-score for rejection of the null hypothesis. Again, I've put this recipe, I've posted it on Blackboard for your reference when you're working through problems. So if alpha is 0.05, you look up the t-score under 95% in the t-table in your textbook. You look up the two-sided or one-sided t-score in the appropriate column, depending on whether your hypothesis test is two-tailed or one-tailed. And again, you use the degrees of freedom to look up the t-score in the appropriate row. If your hypothesis test is one-tailed, then you want to make the critical value of the t-score negative if your alternate hypothesis is left-sided. So remember, if it's that the population mean is less than some specified value. The next step is to compute the t-statistic. The t-statistic is equal to the sample mean minus the population mean, or whatever value you've specified there, divided by the sample standard deviation which is divided by the square root of the sample size. So if your computed t-statistic that you've computed is greater than the critical value of t that you looked up in the table, then you reject your null hypothesis. If your alternate hypothesis is left-sided, then you reject the null hypothesis if the t-statistic is less than that critical value of t that you've looked up in the table. So walking through an example, we have the 10 US states with a percentage of obese adults in the sample of 28.1. The population has a prior mean of 25, and our sample standard deviation is 3.5. And so we want to know, is the percentage of adults who are obese greater than 25? Has the population mean changed? So this is a one-tailed, right-sided alternate hypothesis that the population mean is greater than 25%. The null hypothesis is that it's less than or equal to 25%. Our alpha value is 0.05, and so you can see we have the other test values there. The critical value, the important thing is, at that alpha value of 0.05 and degrees of freedom equal to 9, because degrees of freedom are 10 minus 1, the critical value for the t-statistic is 1.833. So the next step is to actually compute the t-statistic itself using our sample values and population values there. And so we get a result when we plug in the sample mean of 28.1, work it through the equation, we get a t-statistic of 2.8. And our t-statistic, 2.8, is greater than the critical value that we looked up in the table. And so that means we reject the null hypothesis, and we conclude the percentage of adults who are obese has increased to greater than 25% in the population. Okay, so a related form of hypothesis testing is if we measure the same group twice at two different points in time. And this is typically done for pre and post studies. You weighed yourself, went on a diet, and then weighed yourself again. That would be a good example. And so what we're comparing now are mean differences from, which is symbolized by the little bar over the D, equal to the mean difference between time 1 and time 2. Our assumptions are that the mean difference score, D bar, is normally distributed with the variances unknown. And so when it comes to formulating hypotheses, we use the little Greek symbol delta to mean the population difference, whereas D bar is the sample difference. So again, we can have three different kinds of hypotheses. One is that our alternate hypothesis is that the difference is less than 0, so our null would be that it's greater than or equal to 0. If our alternate hypothesis is that the difference is greater than 0, the null is that it's the mutually exclusive alternative, less than or equal to 0. Or our alternate hypothesis might be that the difference is just, it's different, so not equal to 0. And then the null hypothesis is that the difference is null, equal to 0. The t-test is equal to the mean difference, so that the difference between the two means minus 0 over the sample standard deviation divided by the square root of n. And so the sample standard deviation is calculated a little differently here. It's actually the sum of the square, so you need to calculate the sum of squares of the differences. So it's, if you had a bunch of observations listed, difference 1 minus the mean, difference 2 minus the mean, and then all of that. That's squared and summed, just like you did with the sum of squares for x, except now we're looking at the differences here. And then that's divided by n minus 1, and we take the square root of that and then plug that into the t-test. So I've also posted a recipe online in the document that's going to be posted on Blackboard for this. But again, just to go over it briefly here, you set up the null hypothesis and alternate hypothesis. And then you want to compute the difference in your sample means to get d bar. It's pretty straightforward to compute that if you have the two sample means. Then you want to compute your standard deviation of differences. And so you can see the formula for that there. And then you want to choose your desired alpha value. And so typically that's alpha 0.05. Pick your degrees of freedom. And then the next step is, just like we did before, identify the critical value of the t-score for the rejection of the null hypothesis. So this is no different than before for finding the critical value of the t-score. The next step is computing number 7, the t-statistic, which again is a little different for the differences. And once you've computed the t-stat, if it's greater than the critical value of t that you looked up in the table, then you reject the null hypothesis. Again, remember, if your alternate hypothesis is left-sided, then you want to reject the null only if the t-statistic is less than the critical value of t. So let's walk through an example here. Let's say we have a sample of 165 patients who were tested pre and post intervention. Let's say it was a dietary intervention, and the mean change in their body mass index from pre to post is negative 1.23. So their body mass index went down. The sample standard deviation of differences has already been calculated. That's equal to 0.73. Our question is, has the intervention led to weight loss? So that means our alternate hypothesis is that the difference in the population is less than 0 because it's weight loss, it's negative, so the difference over time is going to be some negative number. So this is a one-tailed, left-sided hypothesis test. Our null hypothesis is that the differences, they either stayed the same or got heavier, so that it's greater than 0. So you can see there we have our alpha level, our mean difference, our sample standard deviation. Our n is equal to 165. That means our degrees of freedom is equal to 164. And so when you plug in those numbers with the degrees of freedom and an alpha, a one-sided alpha of 0.05, you look that up in the t-table in your textbook, which would be one-sided 95% in the column in the textbook. You get negative 1.645 as the t-statistic, and we make it negative here because this is left-sided. And so that's our critical value. When we actually go and calculate the t-statistic for our sample, you can see it plugged into the formula there. We get a value of negative 21.6. And so this value of negative 21.6 is much lower than our critical value of negative 1.645, meaning it's more extreme in the left tail. So we reject the null hypothesis, and in this case conclude that our intervention has indeed led to weight loss. Just real quickly here, it's also possible to construct confidence intervals for the mean difference in the pair design. And so this is the same as the confidence intervals that I showed you for the single group mean. The only difference here is that instead of x bar, you're looking at d bar, so you have to compute the mean differences. And then the standard deviation in the formula is it's the same as the standard deviation that you used in the prior slide for the paired difference hypothesis test. Otherwise, everything else in the formula and the way you compute it using the t-distribution is the same as what you did for the prior confidence interval for normal means and unknown variances.